Oh, okay, I guess it just wanted me to click that. I'm doing one more example, and then I'm gonna have you guys work on an example, and then that's what's left of section 3. And just like I did a week ago, I'm gonna save the one that you get to work on for the end of the class, so that, you know, if you wanna leave when you're done, you can. So I'll get a little bit into section 4, and then we'll go back to that. But first of all, we have some charged sheets that do not show up in the picture because they would clutter things up too much. But you imagine this box surrounding the point where they all cross each other. Anyhow, the important thing is that these charges that I didn't bother to draw create an electric field whose components perpendicular to the surface of the box are as shown. And the question is, based on that, how much charge is inside the box? How many coulombs of charge? Well, this is another exercise in using Gauss's law. The amount of charge inside the box is proportional to the amount of flux passing through the box. So from knowing the field all over each surface of the box, I can find the flux. From the flux, I get the charge, and that's the plan of attack here. So I had my little, I guess it was 5-step process that I was suggesting. And the first couple steps are something about what does the field look like, and pick a Gaussian surface, and all of that is given in the question in this case. So we can jump in at what I was calling step 3. Flux is E times A times the cosine of the angle between them. Well, the components perpendicular to the surface would be parallel to the area vector, which is also perpendicular to the surface. So cosine is just equal to 1. Flux is E times A, which means I'm going to need the area of each square face of the box. The area of a square is the length of its side squared. That's why they call it squaring. The total flux through the box we have to add up the dot product of E and A for each of the 6 surfaces, each of the 6 sides of the box. In each case, the area is the 0.16. I'll factor that out because I don't feel like writing it 6 times. On the left and on the right, E is 800. So 800 times the area on the left, 800 times the area on the right. Front and back, 500 volts per meter. $500 times the area on The left, 500 times the area on the right. For the top and bottom, the cosine factor is equal to -1, okay? For the four sides I've already taken care of, the area vector and the E vector are parallel to each other. Do that in front of the camera. But on the sides where the field points in, E and A are anti-parallel, cosine of 180 degrees. So flux is positive where the field lines point out, flux is negative where the field lines point in. So you add those 6 numbers up, you get 400 times the area. So the total, when you add up all the flux through the entire box, the total is 64 when you measure in SI units. Step 4. Once you've calculated the flux, stick it into Gauss's law. Five, solve for the thing the question asks for, which in this case is the enclosed charge. So just multiply both sides by the permittivity constant. Or if you don't like scientific notation, 0.567 of a nanocoulomb. So as I said a couple minutes ago, we'll come back to that last example 15 or 20 minutes from now, somewhere in that general range. Don't let me forget. I've done that. It gets to be like 5 minutes from the end of the class and it's like, oh, wait a minute. I was going to have you do this other thing. In the meantime, we'll flip a couple pages ahead. And my motor skills for today.
That would be so much fun. It would be totally pointless to waste our time.
Well, actually, most things that are fun are pointless and a total waste of time if you look at them objectively.
It's a productive waste of
Okay, section 4 has a couple of different topics in it, but it starts out with capacitors. A capacitor, well, maybe start out with some background information before we get into all the details here. A capacitor is a device for storing electric charge, okay? I've probably already done this before a couple of times. I kind of like comparing electricity flowing through wires to water flowing through pipes because that's a little more tangible. Electricity is kind of invisible. A battery is like a pump, makes the electricity flow through the wires like a pump makes water flow through the pipes. A resistor is like a little tight spot where the pipe gets narrow, and you could go on like that. A capacitor is like a tank, some sort of a storage tank. Capacitors store electric charge. They have a lot of different applications. Just to mention one, they are part of a power supply, like those that power supply sitting on the counter. Yeah, Exhibit A, right? If you take those apart, well, how you make, you plug it into an alternating current, but you get direct current out, at least of the terminals on the one side there. What makes AC into DC is a device called a diode, okay? Now, the old vacuum tube diodes were probably easier to explain than the modern solid state diodes. What you had is like many types of vacuum tubes, it uses an electron beam. You've got a hot cathode at one end of the tube, and electrons cook off of that. The fact that you keep the filament hot gives them enough energy to escape the surface of the metal. And then there's an accelerating voltage that gets them moving, and I talked about that sort of thing a couple of weeks ago. At the other end of the tube is the anode, which collects those electrons, and the current flows on down some wire from there to whatever goes next. If you apply an alternating current to something like that, where the current flowing through a wire as a function of time looks something like that. You try and send that through a diode, and when the current tries to flow in one direction, no problem. When the current tries to flow back the other way, the other electrode is not hot. No electrons cook off of that. And so when the current is supposed to reverse, it doesn't. So what used to be an alternating current, after you pass it through a diode, becomes pulses of direct current. But what you want for most applications is a nice, smooth direct current rather than pulses of it like that. That's where the capacitor comes in. If you take the lid off that power supply and look inside there, well, one thing you see actually is a little cluster of 4 solid state diodes. That's what they call a full wave rectifier. But after it goes through that, there's a big capacitor, almost not quite the size of a can of vegetables, but it's a pretty hefty capacitor. And that's to smooth it out, okay? If you want comparisons to flowing water again, imagine that I've got a 55-gallon barrel, and I'm coming along throwing water into the top of it in bucketfuls. And I've got a hole drilled in the bottom of the barrel, okay? So throw in some water, throw in some water, throw in some water. What runs out of the hole in the bottom of the barrel? Nice, steady stream, okay? So the capacitor soaks up all the variation. And they're also used in audio systems to filter out, the low frequencies that won't go through a capacitor. You find capacitors on motors sometimes to help them start, like on air compressors or pumps. So there's the relevance of it all. If you want to make a capacitor out of stuff you've got in your kitchen, you get out the aluminum foil and the plastic wrap. And you put a sheet of aluminum foil on your kitchen table, and then you lay a piece of plastic wrap. See, that's for an insulator, so the 2 plates won't touch each other. And then another sheet of aluminum foil on top. And then you can take each one of those sheets of foil and maybe hook each one up to the terminals of a battery with some wires that have alligator clips on them or something like that. Okay, so you've got these 2 parallel metal sheets, and you've got battery run some wires over to this foil with insulator in the middle that you've got on. Anyhow, negative terminal of the battery has electrons all over it. Inside the battery, chemical reactions take place that pump electrons from the one terminal to the other. So it maintains an excess of electrons on one terminal, shortage of electrons on the other. Electrons hate each other. They do not get along. Like charges repel. There's nothing more they want out of life than to get as far away from each other as possible. They what? No, they're nonviolent. They don't want to kill the other electrons. They just want to go away. They just want them out of their life.
That would permanently get it out of there.
You would be a bad electron. The electron police would have to come looking for you. But back to my story here. Electrons are free to move through a piece of metal. So when you hook that up, some of these electrons say to themselves, hey, if I was over there, I could get away from these other guys. And off they go. And every time an electron leaves a battery, one gets drawn in on the other side. So the other terminal is sucking electrons out of the other plate. And this continues for a while until, well, a while being a small fraction of a second. But before very long, the next electron in line, sitting here in the middle of the wire, is repelled just as strongly by the other ones that got there first as it is by the negative terminal of the battery. And at that point, this electron says, oh, what the use? There's electrons on either side of me. I might as well just stay here. And at that point, the capacitor is fully charged. Okay? So there are different geometries, different configurations that you could use for a capacitor. What saves a lot of space, actually, is if you put another layer of plastic wrap on top and then you roll it up. A lot of, at least the larger capacitors that you see on a circuit board are quite often cylindrical in shape. But a parallel plate capacitor is what we like to talk about a lot in introductory courses because the math is simplest. As I've already mentioned earlier, between electrically charged parallel plates, you have a uniform electric field. If everything is constant everywhere, you don't need to integrate. You can just use 9th grade algebra. And it just makes the discussion so much simpler. So between a set of oppositely charged parallel plates, guess I'll move this over. We already have some expressions that I developed over the last couple of weeks. Okay, between parallel plates. In other words, this goes with the picture in the handout. Each plate has an area A. Each plate carries a charge Q, plus Q on one plate, minus Q on the other plate. So Q is the charge on either of the plates, not the total on both of them, which would just be 0. I've already shown this was one of the examples using Gauss's law from the other day. I showed that the field between these parallel plates, assuming you're not too close to the edges, so you can assume the plates are infinite. So from Gauss's law, we have that the electric field between these plates is equal to that And from section 2, we have the electric field between the plates is related to the voltage you've applied to those plates by that. Volts per meter times meters equals volts. So I got just enough time to do example number 1, and then we better go back to that thing at the end of section 3. So let's say you've got these 2 plates, which are 1 millimeter apart, which is really wide compared to most capacitors, which is why the capacitance comes out really small for this. But just to put some easy to work with numbers on there anyhow. The question is, how much charge is stored on each plate if you apply it 1,000 volts? You hook it up to a 1,000 volt power supply. Well, actually, maybe I should have just started over here. Back it goes. Rather than copy all that over again, I'm just going to be combining these 2. It becomes delta V equals put the thing that's equal to E where the E used to be. And then since what the question asks for is Q, rearrange it to solve for Q. Divide both sides by D, multiply both sides by A. Now we'll go over here. Drop numbers into that. Epsilon naught is 8.85 to the negative 12. The area in square meters, you've got 0.01 times 0.01 to the negative 4th of a square meter, 0.0001. A millimeter is 10 to the negative 3 of a meter. .85 times 10 to the negative 10 coulombs. Positive that much on one plate, negative that much on the other. And I want to say a couple more things while I've got all the stuff that it comes from written here on the blackboard. This was for a parallel plate capacitor, but, well, get back to that in a moment. In general, any capacitor, it's going to be something of this same general form that nobody on the screen there can see me pointing at because I don't feel like moving the camera yet again. But if you go back over here to where it said Q equals epsilon naught A over D times delta V. Well, for any capacitor, you're going to have that same general kind of thing where Q equals equals some number times delta V, because twice as much voltage can shove twice as much charge into the capacitor. 3 times as much voltage can shove 3 times as much charge into the capacitor. The charge stored per volt is called the capacitance of the device. So definition. Capacitance, C, charge stored per volt, Q over delta V. I'm pretty sure this is one of those formulas I wanted you to remember, as opposed to the kind you can look up on the formula sheet. If you compare this definition to what we had here in the middle of example number 1, where Q equals some constant times delta V, and this is of the form Q equals C times delta V. Well, in the case of a parallel plate capacitor, this thing in parentheses would be the capacitance. To be precise, parallel plates in a vacuum. Epsilon naught A over D. By comparing the general definition to this thing over here is where that comes from. And the last thing out of my mouth before I turn off the camera is the unit to measure this in. Charge is measured in coulombs. Potential is measured in volts. So Q over V, coulombs per volt, that combination of a unit is called a farad. Farad is a lot of capacitance. One farad capacitors do exist, but much more often you see them in the microfarads or even smaller. Okay, so back a page to that example number 7, I guess I called it. You're supposed to figure out the electric field on the right-hand side of the box there. I'll give you a couple moments to get started before I start looking over shoulders. And of course, I have the usual answers all written out on I made a copy for everybody of the solution.